Hello, friends. Welcome back. Or if this is your first time drifting through these quiet nights with us, welcome home. Some nights the world feels wider than it should, stars breathe slower, time folds in on itself, and the edges of everything soften into something almost like memory. Maybe that's just the mind finally listening to itself. Or maybe it's something older, something that was here long before we learned to name it. Tonight we're going to talk about dust. Not the dust that gathers on forgotten shelves or dances in afternoon light through a window. No. Tonight we're talking about the dust that built you, the dust that remembers dying stars and the birth of worlds, the dust that crossed billions of years of silence just to become your fingertips, your breath, your wonder. You've probably heard it before. That phrase people say so easily, it almost loses meaning. You are made of stardust. It sounds poetic, doesn't it? Almost too poetic to be true. But here's the thing that stops me sometimes late at night when I look up. It's not poetry. It's physics. It's chemistry. It's the most literal truth we've ever discovered about ourselves. Before we drift any further into this quiet, I want to pause for just a moment. If these gentle journeys through science bring you some comfort, some curiosity, or simply a softer place to rest your thoughts, you might like to stay a while. You can gently tap the like button if you'd like, not for me, but so this kind of night can find others who need it. Subscribe if you want more of these whispered stories. And that little bell. You can ring it softly, not for noise, but so the next quiet night knows how to find you again. That's all. No pressure. Just an invitation. Now, let's drift. Imagine, if you can, a single grain of cosmic dust, smaller than the width of a human hair, smaller than the period at the end of this sentence, floating alone, in an ocean of darkness so vast that our minds can barely hold it. This grain has no voice, no light of its own, and yet it carries something extraordinary. It carries time. It carries the signature of a star that died before our sun was even a whisper in the dark. Scientists have found these grains actual physical pieces of dust embedded in meteorites that fell to Earth. Pre-solar grains, they call them. Dust older than our entire solar system. Dust that knew other skies. Let that sit with you for a moment. Right now, in laboratories around the world, researchers hold fragments of stone that contain grains formed in the atmospheres of stars that exploded billions of years ago in a part of the galaxy we will never visit. These grains survived. They drifted through shock waves, through cold, through radiation, through time itself. And then somehow, they became part of us. You don't need to understand all of it. You don't need to grasp the full weight of deep time or the mechanics of stellar nucleosynthesis, not yet. Right now, all you need to know is this: you are not separate from the universe. You are what happens when the universe becomes curious about itself. There's a quiet kind of ache in, that isn't there, to know that everything, the calcium in your bones, the iron in your blood, the oxygen you're breathing right now, was forged inside a star. Not metaphorically. Actually, those atoms were created under pressures and temperatures so extreme that they ripped matter apart and stitched it back together into something new. And when those stars could no longer hold themselves together, when they exhausted their fuel and collapsed or exploded in brilliant violent deaths, they exhaled. They released all the hard-won matter into space, as dust. The story of cosmic dust is not a loud one. It doesn't arrive with fanfare. There are no great declarations, no cosmic announcements. Just the slow, patient accumulation of grains drifting through the dark, touching each other by accident or gravity, sticking together in ways so delicate it almost seems impossible. And yet, from that impossibility, from those tiny, fragile collisions, came planets, came oceans, came you. Think about the ground beneath your feet right now. Solid, dependable. It feels permanent, doesn't it? But that ground is just dust that stopped moving. Dust that found other dust and decided in the language of physics to stay. 4.5 billion years ago, there was no ground. There was no earth. There was only a cloud, a spinning disk of gas and dust, swirling around a young star we would one day call the sun. And in that cloud, in the cold and dark, something extraordinary began to happen. Dust grains no larger than smoke particles started to stick, slowly, carefully, electrostatically at first, just the faintest attraction between surfaces. One grain found another, then another, and another. Over millions of years, those grains became pebbles. Pebbles became boulders. Boulders became mountains floating in space, which we now call planetesimals. And those planetesimals, through collision and gravity and time, became worlds. It's so easy to think of planets as these finished things, isn't it? Like they were delivered fully formed, complete with atmospheres and oceans and continents. But no. Every planet, including this one, was assembled, grain by grain, impact by impact. From a cloud of dust so thin you could pass your hand through it and feel nothing. And yet, given enough time that nothing became everything. Here's what keeps me awake. Sometimes we are still surrounded by that dust. It never stopped. Right now, as you listen to this, approximately 40,000 tons of cosmic dust fall to Earth every single year. 40,000 tons. That's the weight of about 200 blue whales descending silently from space, most of it in particles so small they simply float down through the atmosphere like snow that never melts. You've breathed it in. It's settled on your skin. It's in the water you drink. The past is not behind us, it's still falling grain by grain from the sky. And it's not just inert material. Some of that dust carries organic molecules, the building blocks of life. Amino acids, sugars, complex carbon structures that form in the freezing chemistry of space. When scientists analyzed samples brought back from comets and asteroids, they found molecules that under the right conditions could contribute to the origin of life. Not life itself, not yet, but the pieces, the potential, delivered on the backs of dust grains that traveled for eons through the cold. Do you ever wonder what that means? That the raw materials of life might not be rare, that they might be everywhere scattered across the cosmos, hitching rides on dust, waiting for a warm planet, a stable star, a little liquid water, waiting to wake up. There's a photograph I want you to imagine. It's an image taken by the Hubble Space Telescope of a region called the Eagle Nebula. You might know it as the Pillars of Creation, towering columns of gas and dust, light years tall, glowing at their edges where newborn stars are igniting. Inside those pillars right now, dust is doing what it's always done. It's gathering, clumping, beginning the long, patient process of becoming something else. Somewhere in those pillars in the dark, a grain of dust is meeting another grain for the first time. And maybe billions of years from now, those grains will be part of a world where something wakes up and wonders where it came from. That's the part that gets me, the patience of it, the slowness. We live such short lives. We measure time in hours and years and generations if we're lucky. But dust measures time differently. Dust doesn't hurry, it drifts. And over time scales we can barely comprehend that drifting builds galaxies. There's a concept in science called deep time, the recognition that Earth and the universe beyond it has existed for so long that our human experience of time is almost meaningless in comparison. A human lifetime is a blink. Recorded history is a blink. Even the entirety of human existence, every thought, every word, every civilization is just a thin layer at the very surface of deep time. And beneath that surface, stretching back almost 14 billion years, is the story of dust. I think that's why this feels like a good story for late at night. Because there's something strangely comforting about it, isn't there? To know that we are made of dust, to know that we came from something so small and quiet. It makes the bigness of the universe feel a little less lonely. Because if we are dust, and dust is everywhere, then in a way, we were always meant to be here. Not because of destiny or design necessarily, but because the universe has been preparing the ingredients for a very long time. So, Tonight, as you settle in, as your breathing slows and your thoughts begin to soften, I want you to hold that image, a single grain of dust floating in the dark, no larger than a whisper. And yet, inside that grain, written in its atoms and its isotopes, in the very structure of its crystalline lattice, is the memory of a star that lived, burned, and died so that you could be here wondering about it. We're going to spend this night together, drifting through the hidden life of cosmic dust. We'll visit the places where it's born, where it travels, and where it builds. We'll talk about planets and comets and the glowing disks around distant stars. We'll trace the long, winding path from stellar death to living breath. And maybe by the end, you'll feel what I feel sometimes when I look up at the sky, not smallness, but connection. Not insignificance, but belonging, because you are not standing on Earth looking up at the stars. You are made of Earth, and Earth is made of stars, which means, in the most literal sense, you are the universe looking at itself. You are stardust awake, dust that learned to wonder. And that, I think, is the most beautiful fact I know. So, rest here. Let your mind drift like dust on a solar wind, slow and weightless. You don't need to hold on to every detail. Just let the ideas float past you the way dust floats through the dark between stars, unhurried, unafraid, and somehow exactly where it needs to be. What if everything, every planet, every ocean, every breath you've ever taken began not with a bang, but with a whisper of dust? What if the quietest thing in the universe turned out to be the most important? We're about to find out. But before we do, I want you to take one more slow breath. Feel the air fill your lungs. That oxygen. It was made in a star, the carbon that helps carry it through your blood. Also a star, the iron that makes your blood red, forged in a supernova. You are quite literally breathing stardust right now. And in a moment, we'll trace that dust back to its beginning. To the furnaces where it was born, to the dying stars that gave it shape and set it free into the dark where it would drift for billions of years until it found its way. Here, to you, the dust remembers. Even if we forget, even if we never knew, the dust remembers the light of stars that died before Earth was born. And now that dust is awake. It has eyes, it has questions. It looks up at the night sky and wonders, where did I come from? Let's go find out. Every element heavier than hydrogen was born in violence. Everything you've ever touched, tasted, or loved, forged in the collapse of something that could no longer hold itself together. Stars don't die quietly. They don't fade with grace. When they run out of fuel, they either implode into themselves or they explode outward, seeding the universe with the dust that will one day become everything else. The atoms in your body, right now, carbon, nitrogen, oxygen, iron, they weren't here at the beginning of the universe. The Big Bang gave us hydrogen, helium, and traces of lithium. That's it. Everything else had to be made. And the only factory capable of creating those heavier elements is a star. Inside the core of a star, temperatures reach tens of millions of degrees. At those temperatures, hydrogen atoms fuse into helium. Helium fuses into carbon. Carbon into oxygen. Oxygen into neon magnesium silicon. The star climbs the periodic table element by element, squeezing lighter atoms together to create heavier ones. This process is called stellar nucleosynthesis, and it's the reason you exist. Scientists have traced the isotopic signatures of elements in our bodies back to specific types of stellar events. They can tell you which kind of star made the calcium in your teeth, the phosphorus in your DNA. It's forensic cosmology. The universe left receipts. But here's the thing. Most people don't realize stars can only fuse elements up to a certain point. For stars like our Sun, what astronomers call main sequence stars, fusion stops at helium. They don't have enough mass, enough gravitational pressure to go further. They'll swell into red giants, eventually puff off their outer layers into space and leave behind a dense core called a white dwarf. That's a gentle death, relatively speaking. And in that process, they release dust, Carbon dust mostly. Tiny grains of soot formed in the cooling outer layers of the dying star, carried away on stellar winds. Bigger stars, those stars with 8, 10, 20 times the mass of the sun, they don't stop at helium. They keep fusing. They build oxygen, neon, magnesium, silicon, sulfur. And at the very end, in the final moments of their lives, they create iron. Iron is the end of the line. Fusing iron doesn't release energy, it consumes it. So, when a massive star's core turns to iron, it's doomed. The core collapses in less than a second. The outer layers no longer supported crash inward at a quarter of the speed of light. And then they bounce. The rebound sends a shock wave ripping outward through the star, and the star explodes. A supernova? For a few weeks, that single dying star can outshine an entire galaxy. And in that explosion, in the unimaginable heat and pressure of the shockwave elements, heavier than iron are created. Gold, platinum, uranium, all the heavy elements in the universe, every wedding ring, every coin, every atom of lead were made in supernovae. And those elements don't stay trapped in the explosion. They're blown outward into space mixed with gas and dust, cooling as they travel. That's where cosmic dust is born. In the death throes of stars. In 1987, astronomers witnessed a supernova in the Large Magellanic Cloud, a small galaxy neighboring our own Milky Way. It was close enough, only about 160,000 light-years away, that they could study it in extraordinary detail. They named it SN 1987A. And over the years, as the light from the explosion faded and the debris expanded, something remarkable appeared. Dust. Lots of it. Infrared telescopes detected the unmistakable signature of dust grains forming in the cooling gas. Scientists estimate that SN 1987A produced somewhere between half a solar mass and a full solar mass of dust. That's an almost incomprehensible amount. Enough dust to build hundreds of thousands of Earths. And it's still out there drifting, spreading, mixing with the interstellar medium. Someday, billions of years from now, some of that dust will become part of a planet, maybe even part of something alive. It's one thing to theorize that supernovae create dust. It's another thing entirely to watch it happen. SN 1987. A was proof, a real-time observation of stardust being born. But supernovae aren't the only source. There are other quieter deaths, stars that don't explode, but instead exhale. These are called AGB stars, asymptotic giant branch stars. They're in the late stages of their lives, pulsating unstable shedding, their outer layers in slow rhythmic waves. And in those outer layers, as the gas cools and condenses, dust forms. Not in the chaos of an explosion, but in the gentle drift of a dying star's breath. AGB stars are particularly good at making carbon dust and silicon carbide dust, tiny crystalline grains, with structures so precise they can survive for billions of years. We've found these grains on Earth. Scientists extract them from meteorites using acids that dissolve the surrounding rock, but leave the pre-solar grains intact. Under an electron microscope, these grains are beautiful, geometric, almost delicate. And when researchers measure the isotopic ratios inside them, the numbers don't match anything from our solar system. They're wrong in very specific ways. Ways that tell us these grains came from other stars, stars that died before our sun was born. Some of these grains are older than Earth by hundreds of millions of years. They are quite literally pieces of other skies. There's a particular type of AGB star that fascinates me, carbon stars. They're rare but unmistakable. Over millions of years of fusion, they've produced so much carbon in their cores that it starts to dominate their chemistry. When that carbon-rich gas escapes into the cooler outer layers, it condenses into soot, pure carbon dust. These stars look red to our eyes, sometimes even a deep ruby color, because the carbon dust in their atmospheres absorbs blue light and lets the red through. They're essentially cosmic chimneys, pumping out carbon smoke into space. And that smoke, those grains of carbon, eventually finds its way into molecular clouds where new stars and planets form. Some of the carbon in your cells, the carbon that makes life possible, might have come from a carbon star that died 8 billion years ago. Now, let's talk about something even stranger. There's a nebula called the Crab Nebula. You might have seen pictures of it. It's the remnant of a supernova that exploded in the year 1054, observed and recorded by Chinese astronomers as a guest star that appeared suddenly in the sky and remained visible even during the day for several weeks. Today, the Crab Nebula is a glowing cloud of gas and dust, still expanding outward from that ancient explosion. And astronomers have measured the amount of dust inside it. The numbers are staggering. There's more dust in the Crab Nebula than the total mass of planet Earth. One exploded star produced more dust than our entire world. That's the scale we're talking about. That's the abundance. But here's where it gets even more interesting. Not all dust is the same. Cosmic dust comes in different flavors, different compositions, depending on where and how it formed. Silicate dust, made of silicon, oxygen, magnesium, and iron, is common around certain types of stars. It's similar to the minerals that make up rocky planets. Then there's carbon dust, which forms in carbon-rich environments like those AGB stars we talked about. There's also iron dust, though it's rarer, formed in the hottest, most energetic supernovae. And there are ice-coated grains, dust particles that, out in the cold of interstellar space, accumulate layers of frozen water, carbon dioxide, methanol, ammonia. These icy grains are incredibly important because their surfaces act as tiny laboratories where complex molecules can form. Scientists have identified a type of carbon dust called polycyclic aromatic hydrocarbons, PAHs for short. These are large, flat molecules made of carbon and hydrogen arranged in hexagonal rings, kind of like molecular chicken wire. PAHs form in the cooling gas around dying stars, and they're everywhere. Infrared telescopes have detected PAH signatures in distant galaxies in the space between stars, even in comets. They're survivors, tough, resilient, and they might have played a role in the chemistry that led to life. Some researchers think PAHs could have acted as catalysts, helping simpler molecules link together into amino acids and sugars. There's something almost poetic about that, isn't it? The soot of dead stars drifting through space, accidentally creating the building blocks of biology. Life didn't start from scratch. It started from what was already there, from dust. Another thing to understand about stellar dust, it doesn't form immediately. When a star explodes, the gas is far too hot for anything to condense. Dust only begins to appear later, as the debris cools and spreads. This cooling process takes time, years, sometimes decades. In the case of SN 1987, astronomers didn't detect significant amounts of dust until about 20 years after the explosion. They were watching the nebula carefully using infrared telescopes, waiting to see when and where the dust would appear. And when it finally did, it was like watching alchemy in reverse. Gas turning into solid, vapor into grain, energy into matter that will one day build worlds. Let me give you one more example, because I think it captures the strangeness and beauty of this whole process. There's a star called Betelgeuse. You've probably heard of it. It's the bright red star in the constellation Orion, marking the hunter's shoulder. Betelgeuse is a red supergiant, one of the largest stars we can see with the naked eye. If you placed it where our sun is, its surface would extend past the orbit of Jupiter. It's enormous, and it's dying. Betelgeuse has already burned through most of its fuel. It's in the late stages of stellar evolution, fusing heavier and heavier elements in its core. At some point, could be tomorrow, could be 100,000 years. From now, Betelgeuse will explode. And when it does, it will be visible from Earth, even during the day. A new star appearing suddenly in the sky, just like the one Chinese astronomers saw in 1054. And in that explosion, Betelgeuse will release an unimaginable amount of dust into space. Dust that will drift for millions of years until it joins a molecular cloud somewhere. And maybe some of that dust will end up in a planet, in a tree, in someone's hand. The dust remembers Betelgeuse. Even if Betelgeuse is gone, even if no one is left to see the explosion. The dust carries the memory forward, written in isotopes, in crystal structures, in the ratios of elements locked inside each grain. Death becomes dust. Dust becomes memory. Memory becomes matter. And matter eventually becomes us. Here's the part I want you to sit with for a moment. None of this is rare. None of this is special in the cosmic sense. Stars die all the time. Every second somewhere in the universe, a star is in its final moments. And every second, new dust is being born. Dust that will drift for eons untouched until it finds a place to gather, a place to build. The universe is not running out of dust. If anything, it's accumulating. Every generation of stars adds more heavy elements to the mix, more grains to the clouds. The universe is becoming richer, more complex, more capable of making interesting things, including us. But here's the question that keeps astronomers up at night. How much dust is out there, really? How much of the universe's mass is locked up in these tiny grains? And the answer is, we're not entirely sure. We can detect dust in certain ways by the way it blocks light, by the way it glows in infrared. But there's likely far more dust than we can see directly. Cold dust, dark dust hiding in the shadows between stars. Some estimates suggest that as much as 1% of the mass of a galaxy is dust. That might not sound like much, but when you're talking about galaxies that contain hundreds of billions of stars, 1% is a staggering amount. It's enough to build trillions of planets. And yet dust is fragile. It's constantly being destroyed, blasted apart by starlight, by cosmic rays, by the shock waves of supernovae. Dust doesn't last forever. A grain that forms in the outskirts of a dying star might only survive a few 100 million years before it's vaporized by a nearby star or broken apart by a high-energy photon. So the universe needs to keep making more. And it does. Stars die. Dust forms. The cycle continues. It's been happening for over 13 billion years, and it will keep happening long after we're gone. There's something humbling in that, I think. To know that the dust that made us was once part of a star, and that star was made from dust that came from even older stars. And those stars were made from the hydrogen and helium of the early universe, which came from the Big Bang itself. It's an unbroken chain stretching back to the very beginning, and we are part of it, not separate, not observers, participants. The dust of dead stars awake and aware, looking back at the process that made us and trying to understand it. That's what science is, really. Dust asking questions about dust, stardust studying stardust. It's recursive, circular, and kind of beautiful in a way that makes my chest tighten sometimes when I think about it too long. We are the universe's way of knowing itself. And it all started with the quiet death of stars we will never see in a time before time had meaning. So when you look up tonight, if you can see the stars, remember this: every point of light you see is a furnace, a place where dust is being made, or will be made, or was made long ago. Some of those stars are already dead. Their light is still traveling toward us, but the star itself is gone. Dust now, drifting, waiting for gravity to gather it into something new, waiting to build again. The stars breathe out, and the universe inhales. And in that breath, in that long, slow exchange, everything is created, over and over, without end. That's not a story. That's thermodynamics. That's nucleosynthesis. That's the patient alchemy of time and gravity and heat. That's how dust is born. And now that we know where it comes from, we need to follow it. Out into the cold, into the space between the stars, into the vast quiet dark where dust drifts alone, untouched by light, gathering slowly into clouds. That's where the next part of the story begins. Space is not empty. That's the first thing to understand. We imagine it that way, vast black, silent, with nothing between the stars but vacuum. But that's not quite right. Between the stars filling the gaps, drifting through the dark, is a thin sea of gas and dust called the interstellar medium. And that medium so thin you could pass your hand through it and feel nothing is where everything begins again. The interstellar medium is mostly gas, hydrogen, helium, traces of heavier elements. Roughly 99% gas, but the other 1%, that's dust, and that 1% changes everything. Without it, stars wouldn't form, planets wouldn't exist. Light would travel uninterrupted across the universe, and the sky would look completely different. Dust is the sculptor. It shapes what we see, what we can't see, and what will one day exist. Think about that for a moment. 1%. That's all it takes. 1% dust mixed with 99% gas, and suddenly the universe becomes capable of collapsing into stars, planets, life. It's a reminder, I think, that small things matter, that even the quietest presence can be the difference between everything and nothing. Here's where it gets beautiful. Dust doesn't just float passively in space. It interacts. It absorbs light. It scatters light. It changes the color of everything it touches. When you look at a nebula, one of those glowing clouds of gas often photographed by telescopes like Hubble, the colors you see aren't just from the gas. They're influenced by dust. Blue light gets scattered and absorbed more easily than red light, which is why distant stars often appear redder than they actually are. Astronomers call this interstellar extinction. It's not that the light is truly extinguished, it's just that dust steals some of it, particularly the blue end of the spectrum, leaving the red to travel through. There's a famous example of this one you've probably seen even if you didn't know what you were looking at. The Horsehead Nebula, that iconic silhouette of a horse's head, dark against a glowing background. That darkness isn't empty space, it's dust. A thick, dense cloud of dust so opaque that it blocks all the light from the stars behind it. The nebula itself is estimated to be about 5 light-years tall, unfathomably large, and it's sculpted entirely by the way dust absorbs and redirects light. Behind that dark shape, there are stars. Hundreds of them, maybe thousands. But we can't see them. The dust eats their light before it reaches us. It's like looking at a shadow cast by something invisible. The shadow is real. The thing casting it is hidden. And then there are reflection nebulae which work the opposite way. Instead of blocking light, they reflect it. The Pleiades star cluster. The Seven Sisters is surrounded by faint blue wisps of light. Those wisps aren't gas glowing from the heat of the stars. They're dust reflecting the starlight like fog reflects a street lamp. The dust grains are just the right size to scatter blue light more efficiently than red, so the nebula glows with that soft, ethereal blue. It's an accident of particle size and wavelength, but it's breathtaking. Scientists have studied the way dust affects light so carefully that they've created something called an extinction curve, a graph that shows exactly how much light is absorbed at different wavelengths, and the shape of that curve tells you what kind of dust you're looking at. Silicate dust absorbs light differently than carbon dust. Ice-coated grains have their own signature. By studying how light dims and reddens as it passes through interstellar clouds, astronomers can figure out the composition of dust, billions of light-years away, without ever touching it. They're reading the fingerprints left in starlight. But dust doesn't just change how we see the universe. It changes how the universe behaves. One of dust's most important jobs is cooling. When gas in the interstellar medium gets hot from a nearby supernova, from the shock wave of a stellar wind, it wants to expand. Hot gas doesn't collapse, it spreads out. But if there's dust mixed into that gas, the dust radiates heat away as infrared light. It cools the gas down, and cool gas can collapse. Cool gas can clump together under its own gravity. Cool gas can form stars. Without dust acting as a coolant, star formation would be much slower, maybe even impossible in some regions. Dust is the thermostat of the cosmos. It regulates temperature. It makes creation possible. There's something else dust does that surprised astronomers when they first discovered it. Dust grains aren't spherical. They're elongated, shaped more like needles or rice grains than perfect balls. And when they drift through the interstellar medium, they tend to align themselves with the magnetic fields threading through space. Scientists didn't expect this. They discovered it by accident in the 1940s, when they noticed that starlight passing through dusty regions was polarized, meaning the light waves were vibrating in a preferred direction. The only way that could happen is if the dust grains were lined up all pointing the same way, like iron filings near a magnet. This was one of the first direct pieces of evidence that the interstellar medium has structure, that it's not random. That invisible magnetic fields weave through the galaxy, organizing dust on scales we can barely comprehend. Now, let's talk about what dust is made of out there, floating between the stars. It's not uniform. It's not all the same. Some grains are silicates minerals similar to sand or glass, made of silicon, oxygen, magnesium, and iron. These grains likely formed in the outflows of dying red giant stars and were carried into space on stellar winds. Other grains are carbon-based, graphite amorphous carbon, even tiny diamonds, yes, actual diamond dust, formed in the high-pressure shock waves of supernovae. Then there are PAHs, those polycyclic aromatic hydrocarbons we talked about earlier, flat sheets of carbon rings that glow when struck by ultraviolet light. And finally, there are ice-covered grains. Out in the coldest regions of the interstellar medium, far from any stars, dust grains accumulate layers of frozen molecules, water, carbon monoxide, methanol, ammonia. These icy mantles can be thicker than the grain itself. They're not just ice, they're chemistry labs. Because here's the thing, dust grains are not inert. Their surfaces are active. When molecules in the gas bump into a dust grain, they can stick. And once they're stuck, they're held close together, which makes it easier for them to react and bond. Some of the most important molecules in the universe, molecular hydrogen water, complex organics, form on the surfaces of dust grains. Without dust, the chemistry of space would be much simpler, much less interesting. Dust doesn't just carry molecules, it creates them. In 2013, astronomers using the ALMA telescope in Chile made a remarkable discovery. They were observing a galaxy called A274-4-YD41, of the most distant galaxies ever detected more than 13 billion light-years away. We're seeing this galaxy as it was just 600 million years after the Big Bang, when the universe was still in its infancy. And even back then, even that early, there was dust. Lots of it. Far more dust than anyone expected. This was a problem. A good problem, but a problem. Because dust takes time to form. You need stars to die first to release heavy elements. And then those elements need to condense into grains. The presence of so much dust so early in the universe meant that the first generation of stars must have formed, lived, and died much faster than we thought. Dust was rewriting the timeline of cosmic history just by existing. Here's another strange fact about interstellar dust. It's constantly being destroyed. Starlight can vaporize small grains. Cosmic rays' high-energy particles zipping through space can shatter them. Shock waves from supernovae can blast them apart. The average lifespan of a dust grain in the interstellar medium is only a few 100 million years, which sounds like a long time. But in cosmic terms, it's nothing. The Milky Way galaxy is over 13 billion years old. If dust only lasts a few 100 million years, then the dust we see today isn't the original dust. It's been replaced, remade, generation after generation. New dust forming from dying stars, old dust being destroyed, a constant cycle of creation and loss. And yet, despite all this destruction, the total amount of dust in a galaxy stays relatively stable. There's a balance, an equilibrium. Stars die and make dust. Interstellar processes destroy dust. New stars form from dusty clouds, locking some of the dust into planets. But other stars die, releasing more dust. It's a flow, a circulation. The dust-to-gas ratio in a galaxy, how much dust there is compared to gas, changes slowly over billions of years as the galaxy evolves. Galaxies with lots of star formation tend to have more dust. Galaxies where star formation has slowed down have less. Dust is a tracer. It tells you the story of a galaxy's life. There's a specific type of interstellar cloud that fascinates me: molecular clouds. These are the densest, coldest regions of the interstellar medium, where the gas is thick enough that atoms have combined into molecules. Molecular hydrogen, carbon monoxide, water, ammonia. These clouds are enormous, often hundreds of light years across, containing enough mass to make tens of thousands of stars. And they're dark. Not because there's no light, but because the dust inside them is so thick that visible light can't penetrate. If you were inside a molecular cloud floating in the middle of it, you wouldn't see stars. You wouldn't see anything. Just blackness in every direction. The dust would swallow all the light. It would be the darkest dark you could ever experience. But that darkness is deceptive, because inside those clouds hidden from view, stars are being born. The dust and gas are collapsing under their own gravity, forming dense cores that will eventually ignite as new stars. We can't see this happening in visible light, but infrared telescopes can peer through the dust and watch the process unfold. The Orion Nebula, one of the closest star-forming regions to Earth, is full of young stars still embedded in their dusty cocoons. Some of them are only a few 100,000 years old babies in stellar terms, and the dust around them is already starting to flatten into disks, protoplanetary disks, the beginnings of solar systems. One of the most striking images ever taken is the ALMA telescope's view of HL Tauri, a young star about 450 light-years away. The image shows a perfect disk of dust and gas surrounding the star, with multiple dark gaps carved into the disk. Those gaps are almost certainly caused by planets that are still forming, sweeping up dust as they orbit, clearing lanes like snowplows. This was the first time we'd seen such clear evidence of planets under construction, and the level of detail was stunning. You could see the structure, the rings, the shadows. It looked almost fake, like a rendering, because it was so perfect. But it was real. That's what a solar system looks like before it's finished. A disk of dust patiently arranging itself into worlds. There's a phenomenon called a Bok globule, small, dense clouds of dust and gas, usually less than a light year across, that appear as dark spots against brighter backgrounds. They're named after Bart Bok, the astronomer who first studied them in detail in the 1940s. For a long time, people thought Bok globules were just remnants, leftover scraps of larger clouds. But we now know they're stellar nurseries. Inside many of these dark globules, stars are forming. The dust hides them from view, but infrared observations reveal young stars embedded in the darkness, quietly gathering mass, preparing to ignite. It's a reminder that darkness isn't emptiness. Darkness can be full. Darkness can be the beginning. Here's a question I think about sometimes. How much of the universe is hidden from us by dust? How many stars, how many galaxies are obscured behind clouds we can't see through? We know the center of our own Milky Way is hidden from us in visible light. There's too much dust in the way. If you look toward the constellation Sagittarius, where the galactic center lies, you won't see a bright core. You'll see dark patches, rifts, lanes of obscuring dust. But point an infrared telescope that direction, and suddenly the galaxy lights up. Millions of stars become visible. The supermassive black hole at the center Sagittarius. A star reveals itself. The dust was hiding an entire universe. And it's not just our galaxy. When astronomers study distant galaxies, they have to account for dust. They have to estimate how much light is being absorbed and re-emitted at longer wavelengths. Some galaxies are so dusty that most of their starlight is absorbed and re-radiated in the infrared. These are called sub-millimeter galaxies. And they're some of the most active star-forming galaxies in the universe. They're producing stars at rates hundreds of times faster than the Milky Way. But in visible light, they're almost invisible. The dust hides them. Only infrared and radio telescopes can see them clearly. Dust shapes our view of the universe. It teaches us humility. It reminds us that what we see is not all there is. That light can be bent, blocked, stolen. That absence can be presence. That darkness can be matter waiting. So when you look up at the Milky Way on a clear night, if you're lucky enough to be somewhere dark enough to see, notice the dark patches, the rifts, the places where stars seem to disappear. Those aren't empty. Those are dust clouds, vast and ancient, drifting between us and the light. And inside those clouds, in the cold and the silence, something is happening. Gas is collapsing, dust is gathering, stars are preparing to be born. The space between stars is not a void. It's a medium, a substance. Thin, yes. Almost nothing, yes. But not quite, not empty. And that not quite emptiness is enough. Enough to cool gas. Enough to scatter light. Enough to seed the chemistry of life. Enough to build, given time, everything that will ever matter. And that dust, the dust drifting between the stars, it doesn't stay there forever. Gravity pulls it inward. It spirals. It gathers. It flattens into disks around young stars. And in those disks, something extraordinary begins to happen. Something that seems impossible at first. Something that defies the odds. Dust grains no larger than smoke start to stick together. And from that sticking, from those tiny, fragile collisions, worlds are born. How does something as small as a grain of dust become something as large as a planet? It seems impossible, doesn't it? The gap between a micrometer-sized particle and a world thousands of kilometers across is so vast that your mind almost can't bridge it. And yet, it happens. It's happening right now in disks around young stars scattered throughout the galaxy. Dust becomes pebbles. Pebbles become boulders. Boulders become worlds. But the path from one to the other is far stranger and far more fragile than most people realize. When a star forms, it doesn't consume all the gas and dust around it. Some of that material is left behind spinning in a flat disk called a protoplanetary disk. These disks are enormous, often hundreds of times wider than the distance from the Earth to the Sun, and they're full of dust. Trillions upon trillions of grains, each one drifting in orbit, moving at slightly different speeds, occasionally bumping into one another. Most of the time, when two grains collide, nothing happens. They bounce off each other and keep drifting. But sometimes, just sometimes, they stick. The forces that make dust grains stick are delicate. At the microscopic scale, there's something called the van der Waals force, a weak attraction between molecules that becomes significant when surfaces are very close together. It's the same force that lets geckos climb walls. For dust grains, it's just strong enough to hold two particles together if they collide gently. Not too fast, not too slow. Just right. Scientists estimate that grains can stick together if their relative velocity is less than about 1 meter per second, roughly walking speed. Any faster, and they bounce. Any slower, and they don't meet at all. It's a narrow window, and yet, over time, it's enough. In 2014, astronomers released an image that changed the way we understand planet formation. The ALMA telescope in Chile captured a portrait of a young star called H.L. Tauri, only about 1 million years old. The image showed the protoplanetary disk around the star in extraordinary detail. And what stood out immediately were the gaps, dark rings carved into the disk, concentric circles where dust had been cleared away. Those gaps, scientists believe, are the signatures of planets. Planets that have already formed, sweeping up dust as they orbit, leaving clean lanes behind them like boats cutting through water. The image was stunning. It looked designed, almost artificial, but it was real. It was proof that planets can form quickly within just 1 million years, far faster than older theories predicted. And it was all driven by dust. But here's the problem. The thing that kept planetary scientists awake at night for decades, sticking dust grains together, is hard. Really hard. Once grains grow to about 1 millimeter in size, roughly the size of a grain of sand, they start to bounce instead of stick. This is called the bouncing barrier. When two sand-sized particles collide, they have enough momentum that the van der Waals force can't hold them together anymore. They just bounce off each other, so you're stuck. You can't grow past 1 millimeter. Your planet-building project stalls before it even begins. For years, this was one of the biggest unsolved problems in planetary science. How do you get past the bouncing barrier? How do you go from sand to boulders when physics says you can't? And there's a second problem, even worse than the first. It's called the radial drift barrier. As dust grains grow, they start to feel drag from the gas in the disk. The gas is orbiting the star slightly slower than the dust, because gas feels pressure support that solid particles don't. So, when a pebble-sized particle moves through the gas, it experiences a headwind. That headwind slows it down. And when it slows down, it loses orbital velocity, which means it starts to fall inward toward the star. The math is brutal. A centimeter-sized pebble in a protoplanetary disk will spiral into the star in less than 100 years. 100 years. That's nothing. That's a blink. If you're trying to build a planet and your building materials keep falling into the star before they can grow, you're in trouble. So the question becomes, how do planets form fast enough to avoid this problem? How do you beat the clock? The answer, it turns out, is surprisingly elegant. It's called streaming instability. Here's how it works. Imagine you have a disk full of pebbles all drifting through gas. Most of the time, they're spread out evenly. But occasionally, just by chance, a small region of the disk will have slightly more pebbles than average. That region, because it has more mass, has slightly stronger gravity. And that gravity pulls in nearby pebbles, which increases the mass further, which strengthens the gravity. It's a runaway process. Within just a few orbits, the pebbles can clump together into dense concentrations, dense enough that gravity takes over completely and collapses them into a solid object, a planetesimal, something big enough that it won't drift into the star, something that can survive. Streaming instability bypasses both the bouncing barrier and the radial drift barrier. It doesn't wait for grains to stick together slowly. It gathers them all at once in a gravitational avalanche. And computer simulations show that it works. It can form 100-kilometer-sized objects in just a few thousand years, fast enough to beat the drift, fast enough to build planets. Once you have planetesimals, objects ranging from a few kilometers to a few hundred kilometers across the rest of the process becomes easier. These objects collide and merge. Sometimes the collisions are gentle and the two bodies stick together. Sometimes the collisions are violent and the smaller body is shattered, its fragments scattered. But over time, gravity smooths things out. The largest objects grow faster because they have more gravity, which means they attract more material. This is called runaway growth. A planetesimal that's twice as massive as its neighbors will grow 4 times faster. The big get bigger. The small get absorbed. Within 10 million years, you have planetary embryos objects roughly the size of the Moon or Mars. And within 100 million years, those embryos collide and merge into full-size planets. But there's a twist. Not all planets form the same way. It depends on where you are in the disk. Close to the star, where it's hot, only rocky materials can condense silicates metals, minerals. Volatile materials like water methane, ammonia, they stay gaseous. They don't freeze. So, close to the star, you get rocky planets. Earth, Venus, Mars, Mercury. But farther out beyond a boundary called the frost line or snow line, it's cold enough for water to freeze, and frozen water is incredibly abundant. Beyond the frost line, there's suddenly a lot more solid material to work with. Ice-coated dust grains, water, ice pebbles. And because there's more material, planets can grow much larger. Large enough to capture hydrogen and helium gas from the disk. That's how you get gas giants. Jupiter, Saturn, Uranus, Neptune. They all formed beyond the frost line, where ice was available. The frost line is one of the most important boundaries in a solar system. It determines the architecture. It decides what kind of worlds you get. There's another mechanism that helps planets grow, and it's one of my favorites because it sounds so gentle. It's called pebble accretion. Once a planetary embryo reaches a certain size, maybe a tenth the mass of Earth, it starts to interact with pebbles in the disk in a new way. The embryo's gravity isn't strong enough to capture pebbles directly, but it is strong enough to change their trajectory slightly. Pebbles that pass nearby get deflected. They lose a little energy, and because they lose energy, they spiral inward toward the embryo, not all at once, slowly but steadily. The embryo sits there in the disk, and pebbles just rain down onto it, like a planet eating snowflakes. This process is incredibly efficient. A Mars-sized embryo can grow to Earth mass in less than 1,000,000 years by sweeping up pebbles. And if it keeps growing, if it reaches about 10 Earth masses, it becomes massive enough to start capturing gas. And then you get a gas giant. Pebble accretion explains why Jupiter is so big. It formed fast enough and far enough from the sun that it had time to gather an enormous envelope of hydrogen and helium before the gas in the disk was blown away. Here's something most people don't realize: planet formation is violent. It's not a smooth, orderly process. It's chaos, especially in the final stages when planetary embryos are colliding with each other. These collisions are catastrophic. Imagine two Mars-sized objects slamming into each other at tens of kilometers per second. The energy released is unimaginable. The surfaces melt. Material is vaporized. Sometimes the collision is so violent that the two bodies don't merge, they shatter, and the fragments recollapse under their own gravity into something new. Earth, the planet we live on, was almost certainly hit by a Mars-sized object about 4.5 billion years ago. We call that object Theia. The collision liquefied Earth's surface. It threw an enormous amount of debris into orbit, and that debris eventually coalesced into the moon. The moon exists because of a collision, because of violence, because planet formation is messy. And it's not just Earth. We see evidence of giant impacts throughout the solar system. Mercury has an unusually large iron core, probably because a massive collision stripped away much of its rocky mantle. Uranus is tilted on its side. Its rotation axis is nearly parallel to its orbit, likely because it was hit by something huge early in its history. Venus rotates backward, spinning clockwise instead of counterclockwise, possibly due to a glancing blow that reversed its rotation. Collisions shape the planets. They didn't just build them, they sculpted them. They gave each world its unique character. There's a timeline to all of this. From the moment a protoplanetary disk forms, you have maybe 10 million years before the gas is gone. Stellar winds, radiation pressure, and the intense ultraviolet light from the young star gradually blow the gas away, dispersing it back into space. Once the gas is gone, you can't make gas giants anymore. You can still make rocky planets. Those can take up to 100 million years to fully form, but the gas giants have to form fast. They're on a deadline, and that's why gas giants are relatively rare in planetary systems. You need the right conditions. You need to be far enough from the star that there's plenty of ice. You need to grow fast enough to capture gas before it's gone. It's a narrow window, and yet we've found thousands of exoplanets around other stars, and many of them are gas giants, which means this process, as delicate as it is, happens often, all across the galaxy, dust to worlds, over and over, a cosmic assembly line that's been running for billions of years. One of the strangest discoveries in recent decades is that planets can move. They don't stay where they formed. Early in a planet's life, while there's still gas in the disk, the planet can interact with that gas through gravity. It creates spiral waves in the disk, which exert torques on the planet, changing its orbit. Usually, this causes the planet to migrate inward, spiraling slowly toward the star. This is called planetary migration, and it explains a lot of weird things we see in exoplanet systems. Hot Jupiters, for instance, gas giants orbiting extremely close to their stars, closer than Mercury is to the Sun. These planets couldn't have formed there. It's too hot. All the volatile materials would have been vaporized. So they must have formed farther out and then migrated inward, stopping just before they fell into the star. Why they stopped is still debated. Maybe they ran out of gas to interact with. Maybe they were caught in a resonance with another planet. But the fact that they moved at all tells us that Planetary systems are dynamic. They're not static. They evolve. Planets jostle for position. Some move inward. Some get ejected entirely, flung out of the system by gravitational interactions. Planet formation doesn't end when the disk disappears. It continues for millions of years, with orbit-shifting collisions, happening systems settling into their final configurations. Here's a thought that stops me. Sometimes we are living on one outcome out of countless possibilities. Earth could have been hit by a different object. It could have formed closer to the sun or farther away. It could have migrated inward and been consumed. It could have been ejected into interstellar space. The fact that we're here on a rocky planet at just the right distance from the sun with liquid water and a stable climate, it's not inevitable. It's contingent. The result of billions of small, random events that happen to align in a particular way. Planet formation is a probabilistic process. You start with the same ingredients, gas and dust, but you end up with an incredible diversity of outcomes. Some systems have hot Jupiters, some have super Earths, some have nothing but asteroids. Every system is unique. Every planet is an accident, a beautiful, improbable accident. And yet, for all its randomness, there are patterns, regularities. The frost line creates a natural division between rocky and icy worlds. Planetary migration tends to move planets inward, not outward. Giant impacts tend to happen early during the final stages of accretion. These patterns give us clues. They help us understand not just how our solar system formed, but how all planetary systems form. And as we study more and more exoplanets, as we gather more data, the picture becomes clearer. Dust gathers, gravity pulls, collisions happen, worlds emerge. It's a story written in physics, predictable in its broad strokes, chaotic in its details, and endlessly varied. So, when you look at the ground beneath your feet, solid, stable, ancient, remember it was assembled, grain by grain, pebble by pebble. Over millions of years, in a disk of dust around a young star, particles collided and stuck, grew and merged until they became something massive enough to hold itself together. The ground beneath you is not a given. It's a construction, a slow accumulation of dust that somehow, against all odds, became a world. But dust didn't stop there. It didn't just build planets. It delivered something else, something even more important. Because mixed in with that dust, coating the surfaces of grains, frozen into icy mantles, there were molecules. Organic molecules. The building blocks of chemistry. The ingredients of life. And when those dust grains rained down onto the young Earth, they brought those molecules with them. Dust didn't just build the stage. It delivered the actors. And that story, the story of how dust became life, that's where we're going next. There are pieces of other stars inside you right now. Not metaphorically, actually. Atoms that were forged billions of years ago in places so distant, we will never see them have found their way into your bones, your blood, your breath. And we know this because we can still find them, physical fragments of the ancient dust that built our solar system, preserved in stones that fell from the sky. Every year, thousands of meteorites land on Earth. Most are small, many go unnoticed, but some are extraordinary. They're time capsules, fragments of the original material that condensed around the young sun 4.5 billion years ago. And when scientists analyze these rocks in laboratories, grain by grain, atom by atom, they find something astonishing: dust, older than the Earth itself. Pre-solar grains, tiny crystals of silicon carbide, graphite diamond, formed in the atmospheres of stars that died before our solar system even existed. These grains survived the supernova that destroyed their parent star. They drifted through interstellar space. They became part of the cloud that collapsed to form the sun. They were incorporated into asteroids. And now, after billions of years, they're here, on Earth, in our hands. Think about what that means. You can hold a microscopic grain of dust in a laboratory, a speck so small you need an electron microscope to see it and measure its isotopic composition. And the ratios will be wrong. The proportions of different isotopes won't match anything from our solar system. They'll match the theoretical predictions for what should form in a red giant star, or an AGB star, or a supernova. Each grain carries a signature, a fingerprint, that tells you exactly where it came from. Scientists have cataloged thousands of these pre-solar grains, sorting them by type, by origin, by age. Some are more than 7 billion years old, older than the sun, older than the Earth, older than anything else we've ever touched. They are quite literally pieces of ancient starlight, solid and real and here. In 2006, NASA's Stardust mission returned to Earth after a 7-year journey to Comet Wild 2. The spacecraft had flown through the comet's tail, capturing dust particles in a special aerogel, a material so light and porous that the grains could be slowed down gently without being destroyed. When scientists analyzed the samples, they found something unexpected: amino acids. Glycine, specifically the simplest amino acid, one of the building blocks of proteins. It wasn't contamination. The isotopic signature confirmed it came from the comet, which meant that comets, those icy wanderers from the outer solar system, carry organic molecules. The chemistry of life drifting through space waiting to be delivered. And Wild 2 wasn't unique. In 1969, a meteorite fell near the town of Murchison in Australia. The Murchison meteorite is one of the most studied rocks in the world because it's full of organic material. Scientists have identified more than 70 different amino acids in the Murchison meteorite. 70. For comparison, life on Earth uses only about 20 amino acids to build proteins. The meteorite contains amino acids that biology never invented, molecules that formed in space through processes that have nothing to do with life, delivered to Earth on a rock that survived atmospheric entry and landed in a field. When researchers first realized what they were looking at, when they understood that space was not sterile, that it was full of complex chemistry, it changed the conversation about the origin of life. Maybe life didn't start from scratch. Maybe it had help. Maybe the raw materials were already here, delivered by dust and ice from the outer reaches of the solar system. Here's the thing people often misunderstand. When we say Earth was bombarded by comets and asteroids in its early history, it sounds destructive, violent, and it was. But those impacts also brought water. They brought carbon. They brought nitrogen, sulfur, phosphorus, all the elements necessary for life. Earth formed in the inner solar system, where it was too hot for volatile materials to condense. So, where did our oceans come from? Where did the atmosphere come from? The answer, at least in part, is dust and ice from beyond the frost line. Comets, asteroids, chunks of rock and ice that formed in the colder outer regions, and then migrated inward, colliding with the young Earth, adding layers of volatile-rich material to the surface. Every ocean wave, every raindrop might have started as ice on a comet billions of years ago. Water delivered by dust. There's a particular type of inclusion found in some meteorites that fascinates me. They're called Ca, is calcium aluminum rich inclusions. These are small, often just a few millimeters across, but they're incredibly important. Ca are the oldest solid materials in the solar system. Radiometric dating puts their age at 4.567 billion years, which makes them about 1 million years older than Earth. They formed in the hottest part of the protoplanetary disk, close to the young sun, where temperatures were high enough to vaporize rock. And then, as the disk cooled, the vapor condensed directly into solid crystals, a process called condensation. Ca are the first solids, the first dust grains that formed in our solar system. Everything else came later. When you hold a meteorite that contains Ca, you're holding the beginning, the first breath of matter in a newborn solar system. And then there are chondrules, small round beads of once molten rock embedded in certain types of meteorites called chondrites. Chondrules are strange. They clearly melted and then cooled, rapidly freezing into glassy spheres. But what melted them? They formed in the protoplanetary disk, in a region where there shouldn't have been enough heat to melt rock. Scientists have proposed dozens of explanations. Shock waves from the collapsing gas, lightning in the disk, magnetic reconnection events. We still don't know for sure. But we know chondrules are common. Most primitive meteorites are full of them. And their existence tells us that the early solar system was not a calm place. It was dynamic, energetic, full of processes we're still trying to understand. Chondrules are puzzles frozen in stone, waiting for us to solve them. Here's another fact that feels almost magical every day the Earth gains mass. Not much about 40,000 tons per year, as we mentioned earlier, but it's constant. Micrometeorites, cosmic dust, tiny fragments of comets and asteroids all raining down from space, settling onto the surface. Most of these particles are smaller than a grain of sand. They drift down through the atmosphere so gently that they don't burn up. They just float, and eventually they land. On rooftops, in oceans, on glaciers where they accumulate in layers that scientists can study like tree rings, each layer representing a different period in Earth's history. Some of these micrometeorites are pristine. They've barely been altered since they formed in the early solar system. Others carry traces of organic molecules, amino acids, even sugars. The sky is still delivering the ingredients of life every single day. It never stopped. In 2020, the Japanese spacecraft Hayabusa 2 returned samples from an asteroid called Ryugu. The samples were pristine, collected without contamination, stored in a sealed capsule brought back to Earth for analysis. And when researchers examined them, they found something extraordinary. Uracil, one of the 4 nucleobases that make up RNA. RNA is one of the fundamental molecules of life essential for translating genetic information into proteins. And here it was in a rock from an asteroid formed in the cold chemistry of space. Not life, not yet, but one of the pieces, one of the ingredients. Waiting. It's hard to overstate what this means. It means that the building blocks of biology are not rare. They're not a fluke that only happened on Earth. They're cosmic. They form naturally in the cold and the dark, on dust grains and ice-coated particles drifting through space. Life's chemistry is written into the fabric of the universe. It's everywhere, just waiting for the right conditions to wake up. There's a hypothesis called panspermia, the idea that life, or at least the precursors to life, can travel between worlds on dust, on meteorites, on comets. It's an old idea and a controversial one. Some versions of panspermia suggest that fully formed microorganisms could survive the journey through space, protected inside rocks, ejected from one planet, and eventually landing on another. Other versions are more modest, suggesting only that organic molecules, amino acid sugars, nucleobases, are delivered by cosmic dust, giving a head start to the chemistry of life wherever they land. The evidence leans toward the modest version. We've found organic molecules in meteorites, in cometary dust, in interstellar clouds. But we haven't found life, not yet. Still, the fact that the ingredients are out there scattered across the cosmos suggests that life might not be as rare as we once thought. Maybe every planet that forms gets a delivery of organic material from space. And maybe given enough time and the right environment, some fraction of those planets turn chemistry into biology. Here's something I think about: the dust that built Earth came from at least a dozen different sources. Different stars, different supernova events, different regions of the galaxy. We know this because the isotopic signatures don't match. If all of Earth's material came from a single source, the isotope ratios would be uniform, but they're not. Oxygen isotopes in particular vary widely depending on which meteorite you measure. This tells us that the solar system formed from a mixed cloud, a cloud that had been enriched by multiple generations of stars, each contributing their own dust, their own chemistry, their own history. Earth is not made from one star. It's made from many. A patchwork, a collage. Every atom in your body has its own origin story. its own path through the cosmos. Some came from red giants, some from supernovae, some from stars that died so long ago we can't even imagine them. You are not made from one thing. You are made from everything. In the 1950s, a chemist named Stanley Miller conducted a famous experiment. He sealed a flask with water, methane, ammonia, and hydrogen gases thought to represent Earth's early atmosphere, and ran electrical sparks through the mixture to simulate lightning. After a week, the water in the flask had turned brown. When Miller analyzed it, he found amino acids, simple organic molecules formed from inorganic precursors just by adding energy. The Miller-Urey experiment, as it came to be known, was groundbreaking. It showed that the chemistry of life could arise spontaneously under the right conditions. You didn't need biology to make amino acids. You just needed the right ingredients and a source of energy. But here's what's interesting. We now know that Earth's early atmosphere was probably different from what Miller assumed. It was likely dominated by carbon dioxide and nitrogen, not methane and ammonia. And under those conditions, the Miller-Urey experiment doesn't work as well, which raises a question: if amino acids didn't form easily in Earth's atmosphere, where did they come from? And the answer increasingly seems to be space, delivered by dust, carried on meteorites and comets. The chemistry that led to life might not have started on Earth. It might have started in the cold, on the surfaces of ice-coated grains and molecular clouds billions of years before Earth even existed. There's a mystery in biochemistry that no one has fully solved. It's called homochirality. Amino acids come in two forms, called left-handed and right-handed. They're mirror images of each other, chemically identical, but spatially reversed. When you make amino acids in a lab, you get a 50-50 mix of both forms. But life on Earth uses only left-handed amino acids, only one form. Why, no one knows. Some scientists think it's just an accident, a random choice that got locked in early and then couldn't be undone. But others think there might be a physical reason. Certain types of polarized light or magnetic fields or interactions with minerals might favor one form over the other. And interestingly, some meteorites contain amino acids that are slightly enriched in the left-handed form, not 50-50, more like 60-40, which suggests that maybe the preference for left-handed amino acids didn't start on Earth. Maybe it started in space. Maybe the dust that delivered the ingredients of life also delivered a preference, a bias, that eventually became a rule. It's speculation. But it's beautiful speculation. The idea that even the handedness of life, the way our molecules twist, might have been decided by processes that happened in the dark on grains of dust before the sun was born. Here's a fact that makes me pause every time I think about it. You are breathing pre-solar dust right now. Not a lot, just a few atoms per breath statistically. But it's there, mixed into the air, diluted by billions of years of cycling through rock and water and atmosphere, but still present. Carbon atoms that were made in a star 8 billion years ago. Oxygen atoms from a supernova that exploded before the Milky Way had fully formed. You're inhaling ancient starlight, taking it into your lungs, using it to power your cells, and then exhaling it back out. You are part of the cycle, the same cycle that's been running since the first stars died and released their dust into the void. You're not separate from it. You're in it. You're made of it. And that, I think, is the most beautiful thing we've learned from studying cosmic dust. Not that we came from the stars, though we did, but that we're still connected to them. Still part of the process. Still dust moving through the universe, briefly awake. The ground beneath you was once sky. The air you breathe was once locked in stone. The iron in your blood was forged in a supernova. And the calcium in your bones, it condensed from vapor in the dying breaths of a red giant star. You are not standing on a planet looking up at the cosmos. You are the cosmos, temporarily gathered, temporarily aware. Dust that learned to wonder where it came from. But the dust didn't stop at building Earth and seeding it with organic molecules. It kept moving. It's still moving. In the space around Earth, in the orbits of comets and asteroids and the trails left by ancient impacts, dust is everywhere. And that dust, those wandering grains, they have their own stories to tell. Stories of ice and fire, stories of long journeys and sudden arrivals, stories written in the language of motion, of orbits of the slow dance between gravity and velocity. And those stories, the stories of dust in motion, that's where we turn next. There's a kind of molecule that shouldn't exist, but does. It forms in the coldest, darkest places in the universe regions, so far from any star that temperatures hover just a few degrees above absolute zero. And yet, in that frozen darkness on the surfaces of dust, grains smaller than bacteria, chemistry happens. Complex chemistry. The kind of chemistry that billions of years later becomes the foundation for everything alive. These molecules are called polycyclic aromatic hydrocarbons, PAHs, and they might be the most important molecules you've never heard of. PAHs are made of carbon and hydrogen arranged in flat hexagonal rings like molecular honeycomb. They're tough, stable, and they're everywhere. Infrared telescopes detect PAH signatures in distant galaxies, in the space between stars, in the tails of comets, even in the upper atmosphere of Titan, Saturn's largest moon. Scientists estimate that PAHs might account for as much as 10 to 20% of all the carbon in the universe. That's an astonishing amount. More carbon locked in these molecules than in all the stars, in all the galaxies combined. And the strange thing is, we're not entirely sure how they form. They probably originate in the cooling gas around dying stars, carbon-rich stars that puff soot into space. But once they're out there drifting through the interstellar medium, they're incredibly resilient. They survive ultraviolet radiation that would destroy most organic molecules. They survive shock waves. They survive for billions of years. And they carry carbon, the element of life, into every corner of the cosmos. But PAHs are just the beginning. Out in the cold on the surfaces of dust, grains coated in ice, even more complex molecules can form. Water ice, carbon dioxide, methanol, ammonia. These aren't just frozen onto the grain, they're layered molecule by molecule, creating a kind of chemical laboratory on a microscopic scale. And when ultraviolet light from distant stars hits these icy grains, it provides just enough energy to break some of the molecular bonds and rearrange them into something new. Scientists have replicated this process in the lab. They take dust grains, coat them with ice, blast them with UV radiation, and then warm them up to see what forms. The results are remarkable. Amino acids, sugars, even nucleobases, the building blocks of DNA and RNA. The chemistry of life happening on grains of dust in the absence of any living thing. It's spontaneous, it's natural, and it's happening right now in molecular clouds scattered across the galaxy. Here's what I find beautiful about this. Life didn't invent organic chemistry. Organic chemistry invented life. The molecules came first. They were already there, drifting through space, accumulated on comets and asteroids, delivered to planets like Earth during the early bombardment. Life didn't start from scratch. It started from a library of molecules that had been written over billions of years in the dark by the slow, patient work of photons and dust. Life is not an anomaly, it's a continuation. The next chapter in a story that began long before Earth existed. In 1953, Stanley Miller and Harold Urey conducted their famous experiment, which we touched on earlier. They showed that amino acids could form from simple gases when you add energy. It was revolutionary. But here's what they didn't know at the time: space is already doing this experiment, constantly. On a scale so vast, it dwarfs anything we can do in a lab. Every molecular cloud, every protoplanetary disk, every comet and asteroid, they're all running the same experiment, mixing simple molecules, adding energy from starlight or cosmic rays, and producing complex organics. The Miller-Urey experiment didn't discover something new. It rediscovered something the universe had been doing for eons. We caught up to the cosmos. There's a particular molecule that excites astrobiologists: formaldehyde. It sounds toxic, and it is on Earth, it's used as a preservative. But in space, formaldehyde is a precursor to more complex molecules. When formaldehyde reacts with other simple molecules on the surface of an icy dust grain, it can form sugars. Ribose, for instance, the sugar that makes up the backbone of RNA. Ribose is notoriously difficult to make in a lab under prebiotic conditions. It's unstable. It breaks down easily. But researchers have shown that under the right conditions, specifically on the surface of ice-coated dust grains, exposed to UV light, ribose can form and survive, which means that one of the most important molecules for life might have been delivered to Earth, already assembled, courtesy of cosmic dust. The sugar in your DNA. It might have started as frost on a grain, drifting through a molecular cloud billions of years ago. And then there's the discovery from Ryugu, the asteroid sample by Japan's Hayabusa 2 mission. Among the organic molecules found in those pristine samples was uracil, one of the 4 nucleobases in RNA. This was huge. It confirmed that nucleobases, the fundamental units of genetic information, can form naturally in space. They're not unique to Earth. They're not a miracle. They're chemistry. Predictable, reproducible chemistry that happens whenever you have the right elements and the right conditions. Which raises a profound question: if the building blocks of life are common throughout the universe, what does that mean for the likelihood of life elsewhere? If every star system is seeded with amino acids, sugars, nucleobases delivered by the dust and ice that builds planets, then maybe life isn't rare. Maybe it's inevitable. Maybe every habitable planet gets a chemical head start. And maybe the question isn't whether life exists elsewhere, but how often that chemistry makes the leap from molecules to metabolism. There's an idea in origin of life research called the RNA world hypothesis. It suggests that early life on Earth didn't use DNA or proteins, it used RNA for both storing information and catalyzing chemical reactions. RNA is simpler than DNA, more versatile, and it can do things DNA can't. It can fold into shapes that have enzymatic activity. It can replicate itself under the right conditions. And crucially, the building blocks of RNA, those nucleobases, those sugars are exactly the kinds of molecules we find in space on comets and asteroids and dust grains. Which means that the raw materials for an RNA world were probably delivered to Earth from space. Life didn't have to invent RNA from scratch. It just had to find a way to use what was already there, to take the chemistry that had been accumulating for billions of years and organize it into something self-replicating. That leap from chemistry to biology is still a mystery, but the chemistry part, that's solved. The universe makes organic molecules, lots of them, constantly, without any help from life. Here's a fact that sounds almost too strange to be true. There are more organic molecules in the Orion Nebula than there are grains of sand on all the beaches on Earth. The Orion Nebula is one of the closest star-forming regions to us, about 1,300 light-years away. It's a massive cloud of gas and dust, glowing with the light of newborn stars. And when astronomers study it with radio telescopes tuning in to the specific frequencies where organic molecules emit light, they find an astonishing variety: methanol, ethanol, formaldehyde, acetaldehyde, formic acid, dimethyl ether, vinyl alcohol. Over 200 different organic molecules have been detected in interstellar space. Some are simple, just a few atoms. Others are complex with dozens of atoms arranged in intricate structures. And they're all just floating there waiting to be incorporated into a comet, waiting to be delivered to a planet, waiting to become part of something alive. But not all organic molecules are created equal. Some are much more important for life than others. Amino acids, for instance, come in many varieties, but only 20 are used by life on Earth. And of those 20, only a handful are truly essential. You can't make proteins without them. Glycine is the simplest, just two carbons, an amine group, and a carboxyl group. It's been found in comets and meteorites and interstellar clouds. It's everywhere. Alanine is slightly more complex with an extra carbon, also common in space. But as you move to more complex amino acids, tyrosine, tryptophan, histidine, they become rarer, not because they can't form in space, but because they're less stable. They break down more easily under UV radiation. So, there's a bias. The organic molecules that survive the journey through space tend to be the simpler, more stable ones, which might explain why life on Earth uses the amino acids it does. They're not arbitrary choices. They're the ones that were most abundant, the ones that got delivered in the largest quantities. Life worked with what was available. There's another strange detail about the amino acids in meteorites. They're not quite 50-50 between left-handed and right-handed forms. In most chemical reactions, you'd expect a perfect split. But in some meteorites, there's a slight excess of left-handed amino acids, maybe a few percent more than right-handed. Scientists have proposed several explanations for this. One involves circularly polarized light, whose electric field spirals in a particular direction. If a molecular cloud is exposed to circularly polarized light from a nearby neutron star or a reflection nebula, that light can preferentially destroy one form of amino acid while leaving the other intact. Over millions of years, this could create an imbalance, a bias toward left-handed molecules. And if that biased mixture was then delivered to Earth, it might explain why life chose left-handed amino acids, not by accident, not by random chance, but because the universe, through its physics, through its light and its dust, had already made a choice. It's speculative, but it's testable, and it's beautiful in a way that even the handedness of life, the chirality of our molecules, might have been written into the cosmos long before life existed. There's a concept in chemistry called autocatalysis, a reaction that speeds itself up. The products of the reaction catalyze the reaction, creating more product, which catalyzes more reaction in a runaway loop. Autocatalysis is important for the origin of life because it's one of the few ways you can get self-replicating systems from simple chemistry. And interestingly, some of the organic molecules found in space, particularly certain types of aldehydes and sugars, can participate in autocatalytic reactions. They can, under the right conditions, make copies of themselves. Not perfectly, not reliably, but enough that over time, with enough molecules and enough chances, something interesting might happen, something that crosses the line from chemistry to biology, from molecules that react to molecules that replicate, from dust to life. Now, let's talk about panspermia, again, but more carefully this time. The idea that life could travel between worlds is old, dating back at least to the ancient Greeks. But it gained scientific credibility in the late 20th century when researchers realized that rocks can be ejected from planets by asteroid impacts, travel through space for millions of years, and then land on other planets. We know this happens because we've found meteorites on Earth that came from Mars. Actual pieces of the Martian surface blasted into space by impacts that eventually fell to Earth. And if rocks can make that journey, could microbes protected inside a rock survive the radiation, the cold, the vacuum, and then seed a new world? It's possible. Some bacteria can survive in a dormant state for millions of years. Some can withstand radiation levels far higher than anything on Earth's surface. They're called extremophiles, and they've expanded our understanding of what life can endure. But even if panspermia is possible, it doesn't answer the big question: where did life start? It just moves the question somewhere else. If life on Earth came from Mars, where did Martian life come from? If it came from another star system, where did that life originate? Eventually, you have to explain how life began from non-life, from chemistry, from dust. And that's where the real mystery lies. Not in whether organic molecules are common, they are. Not in whether they can form complex structures, they can. But in how those structures become alive, how chemistry becomes biology, how a collection of molecules reacting on the surface of a dust grain or in a tidal pool or in a hydrothermal vent organizes itself into something that can replicate, that can evolve, that can respond to its environment. We don't know, not yet, but we're getting closer. Every meteorite we study, every comet we sample, every molecule we detect in space adds a piece to the puzzle. And the picture that's emerging is this life is not separate from the universe. It's not an accident that happened once on one planet by sheer luck. It's a natural consequence of chemistry. Chemistry that's been happening for billions of years in the dark on dust. Life is what happens when the universe wakes up. When carbon, nitrogen, oxygen, hydrogen elements forged in dying stars find each other in the right proportions in the right environment and start to move with purpose, start to metabolize, start to replicate, start to remember. You've probably heard the phrase, "We are stardust." It's true, but it's not the whole story. We're not just stardust. We're the stardust that carried organic molecules. The stardust that was coated in ice blasted by UV light, delivered to a young planet by comets and asteroids. We're the stardust that had chemistry happen to it, that accumulated amino acids and sugars and nucleobases over billions of years of drifting through the cold. We're not just atoms, we're organized atoms, atoms that have been through a process, a long, slow, patient process of cosmic chemistry. And that process, that accumulation of complexity, is still happening right now. On dust grains and molecular clouds, on comets and distant solar systems, on planets we'll never see. The universe is still making the building blocks of life, still delivering them to worlds, still running the experiment over and over, without end. And here's the part that keeps me up. Sometimes we don't know where the boundary is. Between chemistry and biology, between molecules that react and molecules that are alive. Is a virus alive? It can replicate, but it needs a host. Is a prion alive? It can propagate, but it's just a misfolded protein. Where does life begin? And could there be other forms of life forms that don't use DNA or RNA or proteins that we wouldn't even recognize as alive because they're so different from what we know? Could there be chemistry out there in the dark, on dust grains, or in subsurface oceans, or in the atmospheres of gas giants that crosses the line into something self-sustaining, something evolving, something alive, but in a way we've never imagined? Maybe we won't know until we look, until we send spacecraft to Europa, to Enceladus, to Titan. Until we analyze the atmospheres of exoplanets and search for the chemical signatures of metabolism, until we check. Because the universe has been running this experiment for billions of years, and we've only just started paying attention. The dust didn't stop at delivering organic molecules to Earth. It kept moving. It's still moving. Dust from comets, dust from asteroids, dust from the slow erosion of worlds. Some of that dust stays in orbit, creating faint halos of particles around planets and moons. Some of it drifts inward, pulled by the sun's gravity. Some of it escapes, blown outward by solar wind, returning to the interstellar medium from which it came. Dust is not static. It's part of a cycle, a circulation, from stars to space to planets and back again. And in that circulation, in that constant motion, dust shapes everything. The orbits of comets, the light of zodiacal glow, the trails we call meteor showers. Dust is the traveler, the wanderer. And its journeys across solar systems, across time, those journeys have stories worth telling. Stories of ice and fire, of collisions and near misses of light reflected and absorbed. And those stories, the stories of dust in motion, are what we follow next. Every August, if the skies are clear, you can watch the Perseid meteor shower. Dozens of bright streaks per hour, sometimes more flashing across the darkness and disappearing in less than a second. People call them shooting stars, but they're not stars at all. They're dust. Tiny grains most, no larger than a grain of sand left behind by a comet that passed through the inner solar system more than 1,000 years ago. When Earth's orbit intersects the trail of debris, those grains slam into our atmosphere at over 130,000 miles per hour. The friction heats them to thousands of degrees. They vaporize. They glow. And for just a moment, a speck of ancient dust becomes a streak of light bright enough to see from the ground. Every shooting star you've ever wished on was a piece of a comet saying goodbye. Comets are some of the oldest, most pristine objects in the solar system. They formed billions of years ago in the cold outer regions beyond Neptune, where ice could condense and survive. And unlike planets which melted and differentiated and erased their early history, comets stayed frozen, unchanged. They're time capsules, chunks of the original protoplanetary disk preserved in deep freeze waiting. Most comets spend their entire existence in the distant reaches of the solar system, either in the Kuiper Belt, a disk-shaped region beyond Neptune, or in the Oort cloud, a vast spherical shell of icy bodies that extends halfway to the nearest star. These regions are so far from the sun that sunlight's faint temperatures are near absolute zero, and orbits take millions of years to complete. Comets out there are invisible, silent, dormant, but occasionally something disturbs them, a passing star, a gravitational nudge from a giant planet. And their orbit changes. They fall inward, toward the sun, toward the light. And when they get close enough, they wake up. Here's what happens when a comet approaches the sun. The ice on its surface, water ice, carbon dioxide, ice methane. Ice begins to sublimate, turning directly from solid to gas without melting. This gas carries dust with it, lifting particles off the surface and releasing them into space. The gas and dust form a glowing cloud around the comet's nucleus called a coma. The coma can be enormous, sometimes larger than Jupiter, even though the solid nucleus at its center is usually only a few kilometers across. And as the comet continues its journey, solar wind, the stream of charged particles flowing outward from the sun, pushes the gas away from the comet, creating a long, straight tail that always points away from the sun. But there's a second tail too, a curved tail made of dust. The dust particles are heavier than gas molecules, so they don't get pushed as easily. They lag behind, curving away from the comet's path, tracing the arc of its orbit. When you see a comet with two tails, one straight, one curved, you're seeing the difference between gas and dust, between light and matter, between what the sun's wind can move and what it can't. For a long time, scientists debated what comets were made of. In 1950, astronomer Fred Whipple proposed what he called the dirty snowball model, the idea that comets were mostly ice with a little bit of rock and dust mixed in. It was a good model. It explained a lot. But when spacecraft finally visited comets up close, they found something different. Comets are not mostly ice. They're more like icy dirt, or maybe dirty ice. The nucleus of a comet, the solid core, is about half ice and half rock and dust by mass. Some scientists joke that comets should be called icy dirt balls instead of dirty snowballs. It's a small distinction, but it matters. It tells us that comets formed in a region where dust was abundant, where rocky material mixed with ice in roughly equal proportions. They're hybrids, neither purely icy nor purely rocky, and because of that, they carry both kinds of material into the inner solar system when they come: water and organics, silicates and metals, everything. In 2014, the European Space Agency's Rosetta spacecraft became the first mission to orbit a comet. The target was 67P/Churyumov-Gerasimenko, a small comet about 4 kilometers across, shaped like a rubber duck. Rosetta spent 2 years studying the comet, watching as it approached the sun, watching as jets of gas and dust erupted from its surface, watching as the coma grew and then faded, and the images it sent back were astonishing. The surface of the comet was not smooth. It was rough fractured, covered in cliffs and boulders and strange pits. Some regions were darker than coal, absorbing almost all the light that hit them. Other regions were more reflective, covered in frost that had condensed from gas released elsewhere on the comet. It looked alien, ancient, like a landscape from the very beginning of the solar system, untouched by time. And in a way it was. The surface of 67P was older than any rock on Earth, older than Earth itself. It had been frozen for 4.5 billion years, orbiting the sun in the cold outer darkness, occasionally making a brief swing through the inner solar system, losing a little material, and then retreating back into the cold. A wanderer, a memory keeper. Here's something strange about comets: they're darker than you'd expect. You'd think that an object made mostly of ice would be bright, reflective, almost white, but comet nuclei are incredibly dark. They reflect only about 4% of the light that hits them, making them darker than asphalt. Why? The answer seems to be that the surface is covered in a layer of dust and organic material, a kind of crust that forms as the ice beneath it sublimates away. The ice turns to gas and escapes, but the dust and rock stay behind, building up over time, insulating the interior, making the comet darker and darker. Eventually, the surface becomes so covered in dust that the comet stops outgassing entirely even when it's close to the sun. It's exhausted. It becomes an asteroid indistinguishable from the rocky bodies that populate the inner solar system. Some asteroids scientists believe are just dead comets, comets that ran out of ice, that lost their tails and became silent, dark, and rocky. Dust covering ice that's no longer there. Now, let's talk about where comets come from. The Oort cloud is almost unimaginable in scale. It's a spherical shell of icy bodies surrounding the solar system, starting about 2,000 times farther from the sun than Earth, and extending out to maybe 100,000 times that distance, nearly a quarter of the way to the nearest star. Astronomers estimate there are trillions of comets in the Oort cloud. Trillions. Most are small, just a few kilometers across, but there might be some much larger dwarf planets, even small planets lurking out there in the dark, too far away and too faint for us to see. We've never directly observed the Oort cloud. We infer its existence from the comets that fall out of it. Every so often, a comet with an orbital period of millions of years appears in the inner solar system, coming from a random direction, following an orbit that's nearly parabolic. These are long-period comets, and they come from the Oort cloud. They're visitors. Most will pass through the inner solar system once and then return to the darkness, not to come back for millions of years. Some will never come back at all. Their orbits will be perturbed by the gravity of Jupiter or Saturn, sending them out of the solar system entirely into interstellar space, where they'll drift forever alone, frozen, carrying a piece of our sun's history into the galaxy. But not all comets come from the Oort cloud. Some come from much closer, the Kuiper belt, a flattened disk of icy objects beyond Neptune. Kuiper belt comets have shorter orbital periods, typically less than 200 years. And they tend to orbit in the same plane as the planets. These are the short-period comets, and they're the ones we see most often. Halley's Comet is a short-period comet returning every 76 years. Comet Hale-Bopp, one of the brightest comets of the 20th century, had a period of about 2,500 years long, but not Oort cloud long. These comets have been captured by the gravity of the giant planets. Their orbits have been bent inward, looped, shortened. They've become regular visitors, appearing on predictable schedules, leaving trails of dust in their wake. And those trails, those streams of particles following the comet's path, are what create meteor showers. When Earth crosses one of these streams, we see meteors. The Perseids come from Comet Swift-Tuttle. The Geminids come from an object called 3200 Phaethon, which might be a dead comet or an asteroid, we're not sure. The Leonids come from Comet Tempel-Tuttle. Every meteor shower has a parent, a comet that passed through, left dust behind, and moved on. Here's something most people don't realize: you can see the dust in our solar system with your naked eye. Not just during meteor showers. Every night, if you're in a dark place far from city lights and you look toward the horizon just after sunset or just before sunrise, you might see a faint pyramid-shaped glow extending up from the horizon along the ecliptic, the plane of the solar system. That glow is called zodiacal light, and it's caused by sunlight reflecting off dust grains in the inner solar system. Millions of tiny particles orbiting the sun, scattering light back toward Earth. The zodiacal light is incredibly faint. You need dark skies to see it, but it's always there. A reminder that space is not empty, that even here in the relatively swept-clean region near Earth, dust fills the void. Dust left behind by comets, by asteroids, by collisions and disruptions that happened thousands or millions of years ago. The dust is still orbiting, still drifting, still catching the light of the sun and throwing it back toward us, a whisper of its presence in the dark. And then there's the asteroid belt, a region between Mars and Jupiter where millions of rocky bodies orbit the sun. Most people imagine the asteroid belt as a dense field of tumbling rocks, like something out of a science fiction movie. But the reality is much emptier. The asteroids are spread out over an enormous volume of space. You could fly through the asteroid belt and probably never see a single asteroid. They're that far apart. But there are a lot of them. Hundreds of thousands have been cataloged. Millions more are too small to track. And they're not all the same. Some asteroids are metallic, made mostly of iron and nickel, probably the cores of larger bodies that were shattered in collisions. Some are rocky, made of silicate minerals, and some are carbonaceous dark carbon-rich objects that contain water and organic molecules. These carbonaceous asteroids are particularly interesting because they're similar to comets. They might have formed in the same region beyond the frost line and then migrated inward, or they might be the remains of comets that lost their ice. The boundary between comet and asteroid is blurrier than we once thought. They're cousins, members of the same family, both made from the dust and ice of the early solar system, both shaped by gravity, by collisions, by the slow grinding of time. In 2017, astronomers detected something unprecedented, an object moving through the inner solar system on a trajectory that didn't match any known orbit. It was moving too fast. Its path was hyperbolic, which meant it wasn't gravitationally bound to the sun. It was passing through. A visitor from interstellar space, the first interstellar object ever detected. They named it Oumuamua, a Hawaiian word meaning scout or messenger. Oumuamua was strange. Its shape was unusual, long and thin, maybe cigar-shaped or pancake-shaped, we couldn't tell for sure. Its surface was reddish, suggesting it was covered in organic material that had been irradiated by cosmic rays for millions of years. And as it passed the sun and began its journey back into interstellar space, it accelerated slightly more than could be explained by gravity alone. Something was pushing it, outgassing maybe. Dust and gas being released from the surface, creating a tiny rocket effect. Or maybe something else. We don't know. Oumuamua moved too fast for us to study it in detail. It came and went within a few months, and now it's gone traveling back into the dark between stars. But it changed how we think about the solar system, because if one interstellar object passed through, there are probably others, maybe many others. Objects ejected from distant planetary systems, wandering the galaxy, occasionally crossing paths with stars like ours. Dust and ice from other worlds visiting briefly silently and then moving on. Micrometeorites, dust particles that survive atmospheric entry, fall on Earth constantly. They're everywhere, on rooftops, in gutters, in the ice of Antarctica. Some scientists collect them from the tops of buildings in cities filtering rainwater through magnets to pull out the iron-rich grains. Others go to remote places, glaciers, desert, the deep ocean floor, where terrestrial dust is rare and cosmic dust stands out. These particles are tiny. Most are smaller than a grain of sand, but they're real. You can hold them in your hand. You can look at them under a microscope. And what you see is extraordinary. Some are smooth spheres melted into glass as they fell through the atmosphere. Others are fluffy aggregates, clusters of even smaller grains stuck together. Some contain iron, some silicates, some organic material. Each one is a piece of the solar system's history. A fragment of an asteroid or a comet broken off, orbiting for millions of years, and then falling to Earth. Every day, tons of this material lands on the surface. We don't notice it, but it's there. The sky is still falling grain by grain the way it's been falling for billions of years. Here's a question I think about sometimes: what role does dust play in shaping the atmosphere? We know that dust grains can act as nucleation sites for water droplets, helping clouds form. Without dust, clouds would be fewer, thinner, less reflective. The climate would be different. And some of that dust, some of those nucleation sites are cosmic. Particles from comets and asteroids falling through the atmosphere, seeding clouds with their presence. It's a tiny effect, but over billions of years, over the entire history of Earth, those tiny effects add up. Cosmic dust might have influenced the climate, might have affected weather patterns, might have played a role, however small, in making Earth the world it is. Dust doesn't just fall, it interacts, it changes things. It's part of the system. Comets are not destroyers. That's the common image: comets as harbingers of doom, objects of fear. And yes, a comet impact would be catastrophic. But comets are also deliverers. They brought water to Earth. They brought organic molecules. They seeded the young planet with the ingredients for life. Every comet that collided with Earth in the first billion years was a delivery, a package from the outer solar system full of volatiles and chemistry. Without comets, Earth might have stayed dry, sterile, barren. Comets are not omens. They're gifts, wrapped in ice and dust, traveling for eons to reach us. And the dust they leave behind, it's still moving, still orbiting, still tracing the paths of comets long gone. Every meteor you see, every streak of light is a connection to that past. To the days when the solar system was young and comets were everywhere, colliding with planets, building atmospheres, delivering oceans. The dust remembers. And when it burns, it tells the story. Bright, brief, beautiful. A piece of the past turning into light. But comets and asteroids, these wanderers of our own solar system, are just the beginning. Because dust doesn't stop at the edge of the solar system. It exists on scales far larger, in the disks around other stars, in the space between galaxies, in regions so vast and so distant that the dust there has never seen a planet. And on those scales, dust doesn't just deliver chemistry or seed clouds. It shapes galaxies. It determines how stars form. It changes the light of the entire cosmos. And that dust, the dust on the largest scales, is where we go next. When you look at a photograph of a distant galaxy, one of those stunning images from Hubble or James Webb, what you're seeing is not the galaxy as it is. You're seeing the light that managed to escape, the light that wasn't absorbed by dust. Because galaxies are full of dust, enormous amounts of it. And that dust changes everything. It dims stars. It reddens their light. It hides entire regions from view. Some of the most active, most violent star-forming regions in the universe are completely invisible in optical light because they're buried behind clouds of dust so thick that not a single photon makes it through. If you want to see what's really happening inside a galaxy, you can't just look at visible light. You need infrared. You need to look at the heat. Because dust, when it absorbs starlight, doesn't destroy that energy, it just transforms it. The light gets absorbed, the dust heats up, and then it re-radiates that energy at longer wavelengths in the infrared. So every dusty galaxy is glowing, not in the colors we see with our eyes, but in the colors that infrared telescopes can detect. A hidden light, a warmth that reveals what the dust is hiding. Astronomers estimate that, on average, about 30 to 50% of all the starlight produced in a galaxy gets absorbed by dust and re-emitted in the infrared. 30 to 50%. That's not a small correction, that's half the light. Which means that if you only look at visible wavelengths, you're missing half the story. You're seeing the stars that are exposed, the regions that are clear, but you're not seeing the dense cores where new stars are being born, where young massive stars are lighting up their surroundings, but can't be seen because the dust is in the way. For decades, this was a problem. Astronomers knew dust was there. They could see its effects the way it dimmed and reddened starlight, but they couldn't see through it. Not until infrared telescopes became powerful enough. And when they finally did, when Spitzer and Herschel, and now James Webb, turned their gaze toward dusty galaxies, what they found was astonishing. Some of the most luminous galaxies in the universe, galaxies producing stars at rates hundreds of times faster than the Milky Way, are almost invisible in optical light. They're hidden behind dust. All that frantic star formation, all that energy trapped and transformed, glowing in infrared wavelengths we couldn't see until recently. There's a class of galaxies called submillimeter galaxies, or SMGs, that are among the dustiest objects in the universe. They're incredibly bright in the far infrared and submillimeter wavelengths, but faint or completely invisible in visible light. These galaxies are producing stars at prodigious rates, sometimes 1,000 solar masses of new stars per year. For comparison, the Milky Way produces about 1 or 2 solar masses of stars per year. SMGs are star factories. And the reason they're so dusty is because all that star formation produces dust. Massive stars live fast and die young, exploding as supernovae within just a few million years, releasing huge amounts of dust into the interstellar medium. And that dust in turn cools the gas, allowing more stars to form. It's a feedback loop. Stars make dust. Dust cools gas. Cool gas makes stars. The cycle accelerates. And the galaxy, for a brief period in cosmic history, blazes with the light of 1 trillion suns, most of it hidden behind a veil of dust, glowing hot in the infrared. But here's the thing about dust. It doesn't last forever on galactic scales. Dust can be destroyed. Starlight can heat it to the point where it sublimates, turning from solid back into gas. Supernova shockwaves can shatter dust grains into smaller pieces or vaporize them entirely. And yet, despite this destruction, galaxies maintain a relatively stable amount of dust over time, which means the dust is being continuously replenished. New dust forming from dying stars. Old dust being destroyed by radiation and shock waves. A balance, a cycle. The dust-to-gas ratio in a galaxy, the fraction of the interstellar medium that's in solid form, depends on the galaxy's history, on how many generations of stars have lived and died, on how much metal astronomers speak for any element heavier than helium has been produced. Young galaxies that formed shortly after the Big Bang have less dust because they haven't had as many stellar generations. Older galaxies like the Milky Way have more. The dust accumulates, slowly, over billions of years. In 2015, astronomers using the ALMA telescope detected a galaxy called A2744-YD4, located more than 13 billion light-years away. We're seeing this galaxy as it was just 600 million years after the Big Bang, when the universe was only about 4% of its current age. And even back then, even that early, there was dust. A lot of dust. Far more than anyone expected. This was surprising because dust takes time to form. You need stars to create heavy elements. You need those stars to die, releasing material into space. You need that material to cool and condense into grains. All of that takes time. And yet, here was a galaxy very young, by cosmic standards already filled with dust. It suggested that the first stars, those massive short-lived population 3 stars that form from pure hydrogen and helium, must have died very quickly. Within just a few 100 million years, they had lived exploded and seeded the universe with enough heavy elements to make dust. The timeline of cosmic enrichment was faster than we thought. Dust was writing the history of the universe in ways we were only beginning to understand. Let's talk about what happens when you try to look at the center of a galaxy. Most galaxies have a supermassive black hole at their core, a black hole millions or billions of times the mass of the sun. And many of these black holes are active, pulling in gas and dust from their surroundings, heating that material to millions of degrees, causing it to glow intensely. We call these active galactic nuclei, or AGN. The brightest AGN are called quasars, and they can outshine the entire galaxy they're embedded in. But here's the problem. Many AGNs are surrounded by a thick torus of dust, a donut-shaped cloud that encircles the black hole. If you're looking at the AGN from the side, edge on all you see is dust. The bright core is hidden. The light is absorbed and re-emitted in the infrared. The AGN is still there, still active, but you can't see it directly. Only when you view it from above or below the torus, looking down the axis, can you see the central engine. This is one reason why AGN come in so many varieties. It's not that they're fundamentally different, it's just that we're viewing them from different angles. The dust changes what we see. It creates the illusion of diversity when underneath the process is the same. There's a galaxy called M82, also known as the Cigar Galaxy, that's a perfect example of what astronomers call a starburst galaxy. It's undergoing an intense burst of star formation, driven by a close encounter with its neighbor, the larger galaxy, M81. The gravitational interaction between the two galaxies compressed gas in M82, triggering a wave of star formation, and the result is spectacular. M82 is producing stars at a rate about 10 times faster than the Milky Way. It's so active that it's blowing hot gas and dust out of the galactic plane in massive outflows called superwinds. You can see these outflows in X-ray and infrared images, huge plumes of material streaming away from the galaxy, driven by the combined force of supernova explosions and stellar winds. And mixed in with that outflowing gas is dust. Dust that formed in the galaxy in the atmospheres of dying stars and in supernova ejecta and is now being expelled into intergalactic space. This is one way that dust escapes galaxies. One way that the material enriched by stellar processing gets spread beyond the galaxy's boundaries, into the space between galaxies where it can eventually be swept up by other galaxies, or remain in the intergalactic medium waiting. Here's something that surprised astronomers when they first measured it. The amount of dust in a galaxy is roughly proportional to its metallicity, the abundance of heavy elements. This makes sense. Dust is made from heavy elements. More metals mean more dust. But the relationship isn't linear. In low metallicity galaxies, galaxies that are young or that haven't had much star formation, there's less dust than you'd expect. The dust-to-metal ratio is lower, which suggests that not all heavy elements condense into dust. Some stay in the gas phase. And the efficiency of dust formation depends on the environment, on the density and temperature of the gas, on how much time there is for molecules to stick together and grow into grains. Dust formation is a delicate process even on galactic scales. It requires the right conditions, the right timing, and not every galaxy provides those conditions equally. Now, let's zoom out further, to the largest scales. Galaxies are not isolated. They exist in clusters, in superclusters, in vast filamentary structures called the cosmic web. And in the space between galaxies, the intergalactic medium, or IGM, there's gas. Extremely diffuse gas, but it's there. And in some regions, there's also dust, not much. The intergalactic medium is far less dusty than the interior of a galaxy. But it's not zero. Dust can escape from galaxies blown out by superwinds or stripped away by interactions with other galaxies. And once it's in intergalactic space, it drifts. It spreads out. It can survive for a long time if it's far from any sources of radiation that might destroy it. Some researchers have even proposed that intergalactic dust might account for some of the dimming of distant supernovae, an effect that was initially attributed entirely to the acceleration of the universe's expansion. It's controversial. The evidence is not conclusive, but it's a reminder that dust is everywhere, even in the voids, even in the spaces we think of as empty. There's a particular wavelength range that's incredibly useful for studying dust, the far infrared and submillimeter. At these wavelengths, dust glows. It's not reflected light, it's thermal emission from the dust itself, heated by starlight and re-radiating that energy. And the beauty of observing at these wavelengths is that you're seeing the dust directly. You're not trying to infer its presence from the way it dims starlight. You're watching it glow. Telescopes like Herschel Spitzer and ALMA have mapped the dust in thousands of galaxies, measuring its temperature, its mass, its distribution. And what they've found is that dust is not uniformly spread. It clumps. It concentrates in spiral arms and star-forming regions in the dense cores of molecular clouds. Dust follows the gas, and gas follows gravity. So, the distribution of dust in a galaxy tells you about the galaxy's structure, about where the mass is, about where stars are forming. Here's a thought that keeps astronomers up at night. How much of the light in the universe have we not seen? Because of dust, we know that dust absorbs and re-emits light. We know that some galaxies are almost invisible in optical wavelengths. But how many galaxies are out there that we've missed entirely? Galaxies so dusty, so buried, that even their infrared emission is faint. We don't know. We're still discovering new populations of galaxies, new types of objects every time we build a more sensitive telescope or observe at a different wavelength. Dust is the great obscurer. It hides things. And every time we find a way to see through it, we discover something we didn't expect. There's a type of galaxy called an ultraluminous infrared galaxy, or ULIRG, that emits more than 1 trillion times the luminosity of the sun, almost entirely in the infrared. These galaxies are rare in the nearby universe, but they are more common at higher redshifts farther back in time, when the universe was younger and galaxies were colliding and merging more frequently. ULIRGs are thought to be the result of major galaxy mergers, where two gas-rich galaxies collide and their gas gets funneled into the center, triggering an intense burst of star formation and feeding the central supermassive black hole. The energy output is staggering, but you can't see it with your eyes, not directly. All that light, trillions of suns worth, is absorbed by dust and re-emitted in the infrared. The galaxy is glowing, but in colors we can't see. Hidden behind a cocoon of dust grains, each one smaller than a bacterium, but collectively capable of absorbing the light of 1 trillion stars. And yet, for all its power to obscure dust, is also a tool, a probe. By studying the dust in a galaxy, astronomers can learn about the galaxy's history, about how many stars have formed, about how much metal has been produced, about the balance between creation and destruction. Dust is a record, a ledger. Every grain carries information about the star that made it, about the supernova that released it, about the molecular cloud that gathered it, about the planet that might one day form from it. Dust is not just matter, it's memory. It's the accumulated history of stellar evolution, written in isotopes and crystal structures and the ratios of elements locked inside each grain. Here's the part that gets me. Galaxies are not just collections of stars. They're ecosystems, complex dynamic systems where gas, dust, stars, and black holes all interact, all influence each other. Dust cools the gas, allowing stars to form. Stars heat the dust, causing it to glow. Supernovae destroy dust, but also create new dust. Dust dims starlight, but also scatters and reflects it. Everything is connected. Everything feeds back into everything else. And dust is at the center of it all. Not the most massive component gas, outweighs dust by about 100 to 1, but one of the most important. Because without dust, the chemistry changes. The cooling changes. The star formation changes. Dust is the catalyst, the mediator, the quiet force that makes galaxies work. So, when you look at an image of a spiral galaxy, when you see those dark lanes running along the spiral arms, remember, those aren't shadows, they're dust. Dust that's blocking the light from stars behind it. And that dust is doing something. It's cooling gas, it's forming molecules, it's preparing to collapse into the next generation of stars. The dark lanes are not empty. They're full of potential, full of the future. But even on these vast scales, even when we're talking about galaxies and superclusters and the cosmic web, we're still only seeing a fraction of the dust that exists. Because there's dust in places we can barely reach. Dust at the edge of the observable universe. Dust around black holes we'll never visit. Dust in galaxies so far away that their light will never reach us. And that unreachable dust, the dust we'll never touch, never see, never measure. That's the dust we turn to now. The dust at the limits of observation. The dust that exists beyond the horizon. The dust that reminds us how much we still don't know. There's dust at the edge of everything we can see. Dust so far away that its light has been traveling toward us for over 13 billion years. Dust that formed when the universe was younger than 1 billion years old, when the first galaxies were still taking shape, when stars were being born at rates we can barely imagine. And that dust, ancient, distant, unreachable, tells us something profound. It tells us that even at the very beginning, even in the earliest moments of cosmic history, the universe was already making the ingredients for worlds, already preparing in its own slow way for the possibility of planets of chemistry of life. The dust didn't wait. It began immediately, and it's still out there at the edge of the observable universe, glowing faintly in wavelengths we can just barely detect, whispering a story about beginnings we will never witness directly. When astronomers look at the cosmic microwave background, the CMB, they're looking at light from about 380,000 years after the Big Bang. This is the afterglow of creation, the moment when the universe cooled enough for atoms to form and light to travel freely for the first time. The CMB is remarkably uniform, almost perfectly smooth, but not quite. There are tiny fluctuations, tiny variations in temperature that tell us about the distribution of matter in the early universe. And when scientists try to map those fluctuations with incredible precision using satellites like Planck, they run into a problem: dust. Not dust from the early universe that didn't exist yet, but dust from our own galaxy, the Milky Way between us and the CMB. That foreground dust emits its own faint glow in the microwave and far infrared, and it contaminates the signal. It's like trying to photograph a distant candle through a dirty window. The smudges on the glass get in the way. So astronomers have to carefully subtract the dust signal, modeling its emission, removing its contribution to reveal the pristine CMB beneath. It's painstaking work. And it's a reminder that even when we're trying to study the universe at its most fundamental level, dust is there, interfering, obscuring, making us work for every answer. But there's also dust around supermassive black holes in places where physics becomes extreme. When gas and dust spiral into a black hole, they form an accretion disk, a swirling disk of material that heats up to millions of degrees as it falls inward. And around many supermassive black holes, there's a dusty torus, a thick ring of cooler material that encircles the inner regions. This dust is close to the black hole within a few light years, sometimes less. And it's exposed to intense radiation, X-rays and ultraviolet light from the accretion disk. The dust absorbs that radiation and re-emits it in the infrared. But here's the strange part. The dust survives. It doesn't vaporize immediately, even though it's bathed in radiation strong enough to ionize atoms. Somehow, it persists. Scientists think the dust might be constantly replenished, destroyed on the inner edge of the torus, but formed again farther out where conditions are cooler. Or maybe the grains are just tougher than we thought, larger, denser, able to withstand more abuse before breaking apart. We're still figuring it out. But the fact that dust exists so close to black holes, objects that warp space-time itself, is astonishing. Dust is resilient. Even in the most extreme environments, it finds a way to survive. Now let's talk about Sagittarius, a star the supermassive black hole at the center of the Milky Way. It's about 26,000 light years away from us, and we can't see it directly in visible light because there's too much dust in the way. The galactic center is one of the dustiest regions in the galaxy. Thick clouds of gas and dust block our view, but in infrared and radio wavelengths, we can see through the dust. And what we see is extraordinary. Stars orbiting incredibly close to the black hole, moving at speeds of thousands of kilometers per second. Clouds of gas and dust being torn apart by tidal forces. Flares of radiation as material falls into the black hole and heats up. And throughout it all, there's dust. Dust in the accretion flows. Dust in the surrounding clouds. Dust that's been there for millions of years, orbiting the black hole, heated and cooled, surviving somehow in one of the most violent places in the galaxy. That dust has a story. It's seen things we can only imagine. And we'll never retrieve it, never touch it. It's trapped there, bound by gravity, circling the black hole until it either falls in or is blown away by an outburst. Unreachable. There's a concept in cosmology called the particle horizon, the boundary beyond which light has not had enough time to reach us. The universe is about 13.8 billion years old, but due to the expansion of space, the edge of the observable universe is about 46 billion light years away. Anything beyond that horizon is by definition unreachable. We will never see it. Not because it doesn't exist, but because the light from it hasn't arrived yet. And in those unreachable regions, there's dust. There must be. Dust forming in stars, in galaxies, in processes identical to the ones we observe here. But we'll never detect it, never measure its composition, never study its structure. It's out there doing what dust does, absorbing light cooling gas, building worlds, but entirely beyond our ability to observe. And that's okay. That's humbling. It reminds us that the universe is larger than what we can see, that there are stories happening in the dark in places we'll never visit, and those stories are just as real as the ones we can study. Here's something that keeps cosmologists awake at night. We don't fully understand how dust formed in the very early universe. In the first billion years after the Big Bang, there shouldn't have been much dust. The first stars. Population 3 stars were made of pure hydrogen and helium. No heavy elements, no metals. And heavy elements are necessary to make dust, so we'd expect the first few 100 million years to be dust-free. But when James Webb Space Telescope started observing galaxies from that era, it found dust. Lots of it, more than expected, far more. Some of these galaxies, less than 1 billion years old, are as dusty as mature galaxies like the Milky Way, which means the first stars must have formed, lived, and died incredibly quickly. Within just a few 100 million years, they enriched the interstellar medium with enough metals to create dust. Or maybe there's another mechanism we don't understand. Maybe dust forms more efficiently than we thought. Maybe there are pathways, chemical routes, physical processes that we haven't discovered yet. The early universe is still surprising us, still teaching us. And dust, once again, is at the center of the mystery. There's a thought experiment I want you to consider. Imagine you could fast forward time. Watch the universe evolve over trillions of years. What would happen to dust stars will keep forming for a while, billions of years, maybe tens of billions. But eventually the gas will run out. Star formation will slow, stop. The last stars will die. And the dust they produce will drift through space, cooling, darkening, until it's indistinguishable from the background. No more starlight to heat it. No more infrared glow. Just cold grains a few degrees above absolute zero, orbiting dead stars or drifting through intergalactic space. And over even longer timescales, 10 to the power of 14 years, 10 to the power of 15 years. Those grains will be eroded by cosmic rays, by collisions with the sparse atoms of the intergalactic medium, by quantum processes we can barely imagine. The dust will decay, atom by atom, until there's nothing left but photons and the faintest traces of matter spread so thin that the universe becomes effectively empty. Dust is not eternal. Nothing is. Even the quietest builders of the cosmos will eventually fade. But for now, for the brief window of cosmic time in which we exist, dust is everywhere. Building, shaping, remembering. Let's come back to the present, to the dust we can study. There's a question that astronomers are still trying to answer: how much of the universe's carbon is locked up in dust? Carbon is one of the most important elements for life, and it's also a major component of interstellar dust. But we don't know the exact fraction. Some carbon is in gas, some is in stars, some is in planets, and some, maybe 10%, maybe 20%, we're not sure, is in dust. That uncertainty matters because it affects our understanding of the carbon cycle in galaxies, how carbon moves from gas to stars to dust and back again, how much is available for planet formation, how much is hidden in forms we can't easily detect. Dust is not just a curiosity. It's a reservoir, a major player in the chemical evolution of the universe. And we're still figuring out how big that reservoir is. Here's a fact that feels almost poetic. The dust we see in distant galaxies is in a very real sense a message from the past. When we observe a galaxy 10 billion light years away, we're seeing it as it was 10 billion years ago. The dust in that galaxy is ancient. And the light from that dust, the infrared glow we detect with our telescopes, left that galaxy billions of years before Earth even existed. That light has been traveling through space for eons, carrying information about a time and place we'll never visit. And now it's here, hitting a telescope mirror, being focused onto a detector, being translated into data, into images, into knowledge. The dust is speaking to us across unimaginable distances, across time, and we're listening. There's a galaxy called GN-ZD11, one of the most distant galaxies ever observed. It's so far away that we're seeing it as it was just 400 million years after the Big Bang. The universe was still in its infancy. And yet, GNZ11 contains dust. Not as much as a modern galaxy, but it's there, detectable, real. That dust formed in the first generation of stars and supernovae that exploded when the universe was less than 500 million years old. And now, more than 13 billion years later, the light from that dust is reaching us. A faint whisper from the dawn of time. A reminder that dust has been part of the story from almost the very beginning. But here's what I want you to remember: most we are part of this story. Not observers, participants. The dust that built Earth, the dust that delivered organic molecules, the dust that makes up your body, it's the same dust, the same process, the same atoms cycling through stars, through space, through planets, through life. You are not separate from the galaxies we've been talking about. You are made of the same stuff. You are dust that woke up, dust that learned to wonder, dust that looks out at the universe and asks, where did I come from? And the answer is everywhere. From dying stars, from molecular clouds, from comets and asteroids, from the slow, patient work of gravity and chemistry and time. And here's the beautiful part: you're not the end of the story. When you die, the atoms in your body will return to the cycle. Some will be buried locked in rock for millions of years. Some will be released into the atmosphere, carried by wind and rain, spread across the surface of the planet. And someday, maybe billions of years from now, when the sun swells into a red giant and the Earth is no more, those atoms will be released back into space. They'll become dust again. They'll drift through the interstellar medium. They'll be swept up by a molecular cloud. They'll become part of a new star, a new planet, maybe a new form of life. The cycle doesn't end. It just continues, over and over. Stars to dust, to worlds, to life, to dust, to stars. Without beginning, without end. Just transformation, just continuation. So, when you look up at the night sky, when you see the stars, remember this: you're not looking out. You're looking back. Back at the furnaces that made you. back at the clouds that shaped you, back at the dust that became you. And in a very real sense, you're looking at yourself, at your past, at your future, because you are the universe, temporarily gathered into a shape that can think and feel and wonder. Dust briefly awake. And maybe that's the most profound thing we've learned from studying cosmic dust. Not that we're small, though we are, not that we're insignificant, though our lives are brief, but that we're connected to everything, to every star that ever lived, to every galaxy that ever formed, to the very fabric of the cosmos itself. We are not separate. We are part of it. We always have been. We always will be. The dust remembers. Even if we forget, even if civilizations rise and fall, even if stars burn out and galaxies fade, the dust remembers. It carries the signature of every process it's been through, every star that made it, every supernova that released it, every planet it helped to build. And someday, long after we're gone, that dust will still be here, drifting, waiting, ready to build something new. So, rest easy. You are stardust. You are ancient. You are rare, and you are common. You are fragile, and you are resilient. You are the universe looking at itself for just a moment before returning to the cycle. And that moment, this moment, is enough. More than enough. It's everything. Thank you for drifting with me through this long, quiet night. Through the story of dust, from the deaths of stars to the birth of worlds, from the chemistry of life to the edges of the cosmos. I hope you found something here that made you pause, something that made you feel a little more connected to the sky, a little more at home in the universe, because you are home. You've always been home. You're made of the same dust that built the stars, and that dust is still here, still moving, still building, still becoming. If you'd like to join me on more journeys like this, more quiet nights, more stories told, softly more science that feels like wonder, I'll be here, ready to drift with you again. Until then, sleep well, dream gently, and remember you are dust that learned to ask questions, dust that learned to love the stars, dust that learned for a brief and beautiful moment to be awake. Good night.